Hey Chem 20s, it's me, Mr. Jukley. We're starting off our very last unit of Chem 20, and we are going to blow through some of this stuff. Like, we're going to go so fast through it. So anyways, our unit here, if you haven't got this one, it is the gases one. You can get it off of Google Classroom if you haven't picked it up from me, but it's all about gases. So properties of gases and also exploring gas laws as we've gone through. Now gases are kind of interesting because you're surrounded by gas all the time, right? The air around you, but you really think about it too much. There's tons of other things that go on in our lives, but again, you don't really think about it that much. Like gases are pretty important, but because they're essentially clear, colorless for the most part, you don't really think about it, which is kind of crazy. So anyways, some properties of gases and our kinetic molecular theory. This is where I would like to start off. Again, I'm going to try and go through this really quickly and cover a whole bunch of stuff here in the next little while. I don't know if that's my favorite color for this. Oh, I like that one today. Yeah, that's a nice color for today. Okay, so jumping in, some properties of gases. Gases are compressible. Compressible, which means when you squish them or you apply pressure, they get smaller. Cool. Liquids, solids, not so much. Gases also expand due to increase in temperature, assuming that we have a constant pressure. Whereas liquids and solids, they also do, but significantly less. Gases expand a lot when you increase temperature. Gases also flow very easily. That being said, they are not viscous materials, so they flow very easily with very little resistance, which allows them to escape from small openings very easily. So just think about a balloon, or unfortunately my paddle board got a hole in it. Lydia and I bought inflatable paddle boards, and just a tiny little hole, and the thing was pretty much empty overnight. Right? They flow easily, very easily. Gases have low densities. Low densities. So, in other words, they typically float on top of liquids and solids and other things. They have higher densities. And as an example, gaseous water is 1/1000th the density of liquid water, so significantly less dense. And then finally, gases are miscible, which kind of means mixable, but very specifically, it's able to form a solution with its own type, so with other gases. So a gas is miscible. It's pretty much any gas can form a solution with pretty much any gas. Now you think liquids are pretty miscible as well. So liquids with liquids, well, some of them are, like alcohol and water, so polar and polar, absolutely miscible. They interact with each other, they dissolve each other, no problem. But there's significantly fewer liquids. So think about alcohol and water, or sorry, think about oil and water, gas and water. Like so many things don't mix very well. Cool. So these are all macroscopic properties that we've talked about before. Before this, up above. So again, defined as fluids, they have no particular shape or no particular volume. They take the shape and volume of any container that they're in, and they actually expand to fill any container. Cool. Next thing we want to talk about is our kinetic molecular theory. So kinetic molecular theory, let's just think about that for a little bit. Kinetic. Kinetic is all about motion. Molecules, all about tiny little pieces. And then theory, our best idea of what we've got for this. So essentially what we've got, gases, and realistically anything, is made out of tiny particles that are in random motion. Random motion. Right? And there's usually spaces in between those. They collide with each other and with other objects in their path. The energy is always released whenever collisions occur. If there's enough energy in those collisions, that's where a chemical reaction takes place. And again, kinetic is all about motion. So kinetic energy is the energy of motion. Cool. So what kind of motion do molecules actually do? Well, there's translational motion, there's rotational, there's vibrational. By the way, I'm going to put this in brackets because you don't necessarily need to know this very well. I mean, it's good to have an idea, but, you know, we'll talk about it, but that's about all. So translational motion. This is the motion of a particle in a straight line. versus rotational, which is the spinning, versus vibrational, which is the back and forth motion, the vibrating of a particle. So 3 different types of motion that particles could individually have. When we talk about solid, liquids, and gases. Solids, definite shape and volume, incompressible, do not flow readily. They mainly have vibrational motion, right? And I think you've talked about that in other courses before. Liquids, they do assume the shape of the container. They're incompressible. They do flow readily. And they got kind of every type of motion, right? Vibrational, rotational, translational, they got it all. And then gases, well, yes, they absolutely do take the shape of the container. They're highly compressible. They flow readily, and it's mostly straight line motion. And that's sort of the big thing, mostly that translational. So in other words, they move in straight lines until they collide with each other or they collide with their container. Cool. So next little piece that we want to talk about here is an ideal gas. So an ideal gas is not actually a real gas, but it's a good way to estimate a real gas, right? And to make some estimations as we go through and we start to look at and explore the properties of real gases. So when we have an ideal gas, the gas particles are in constant motion and they travel in perfectly straight lines until they experience a collision. At room temperature, high temperatures, absolutely no problem. That happens quite often. The molecules are point masses, which means they have mass, but they don't have any volume. At regular, everyday temperatures and pressures, absolutely that's true, because when we think about, well, not true, I shouldn't say that, but close to being true, because when you think about just like the air around you, there is so much empty space that the amount of empty space that we have is significantly bigger than the size of the molecules. So the size of the molecules kind of don't really take up any space compared to the size of the container, right? They do take up a little bit, but not anything significant. Okay, lastly, they collide with one another and the walls of the container in perfectly elastic collisions, which means no energy is being lost in the collisions, which realistically, anytime there's a collision, there's a little bit of energy lost, right? But very, 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 very little when we're talking about gases, and especially when we talk about ideal gases, we're saying that none of it is. So again, estimations. So an elastic collision, all kinetic energy is conserved. They smash into each other and it's the same. So the average kinetic energy, this is something that's kind of important, this last little piece, the average kinetic energy is related to the temperature of the gas. The temperature is based on average kinetic energy of the molecules. Cool. So these properties of the ideal gas explain the macroscopic properties of gases such as miscibility. There's so much space in between them that they have no problem molecule of one gas fitting in with another. Okay, where were we there? So last thing I really want to talk about here is when ideal gases or when real gases are not like ideal gases, and that is at high pressures, and low temperature. So high pressures and low temperatures. And we can kind of think about that, right? High pressures means those molecules are going to be squished together so much that they're going to interact with each other. They might stick to each other. They might not go in perfectly straight lines anymore. There might not be perfect amount of space in between them, or like a ridiculous amount of space in between them. Low temperatures, same sort of idea. They slow down enough that they interact with each other. The collisions are no longer really elastic. They might even stick together, which would be an inelastic collision. The space between them becomes smaller and smaller and smaller, so that means the space of the actual particle becomes more significant. Oops, I think I skipped ahead a little bit too much there. So that is our first little chunk. I should have mentioned before, this might be a bit of a long lesson because we're going to go through a bunch of stuff here. So if you need to take a break now, is probably a good time. The properties of gases worksheet, this is for this group optional, right? So for our COVID-19 group, this is totally optional. You can choose to go through this or not. Some of these are quite challenging, but definitely doable and definitely kind of interesting. They make you think about those things that we've talked about in the previous few minutes. Cool. So again, if you need to take a break, that's cool. Put it on pause. You can come back to it in an hour or 10 minutes or whatever you need. This is a good spot. If you don't need to take a break, well, let's just keep on rolling. All right, so that's more practice, more practice. Okay, next session that we want to talk about is gases and pressure. Now there's a bunch of notes here. We're going to highlight a couple little things here. So when we talk about pressure, pressure is the force per unit area. So force is a push or pull, and area is, well, the area that that force of push or pull is acting on. That is kind of important, right? The difference between force and pressure is that force is one direction, only in one direction, and it's only typically one thing. Whereas pressure, you could have a bunch of forces acting over a larger area, acting in all directions. But pressure is force per unit area. Cool. The pressure is actually exerted by the moving gas molecules as they collide with the walls of their container, essentially. So when we think about this, here's a container, very nice, and I've got gas particles. They're moving in all different directions. They are smashing into the walls of the container. So each one has its own individual force in the wall of the container. The more of those collisions we have, the more forces we have, the harder those collisions are, the more force we have. And then the area is obviously the area of the container. So we'll come back and we'll talk about this a little bit more. Units that we're going to use for this, the most common one is probably kilopascals, to be honest. When we talk about 1 Pascal, it's 1 Newton per meter squared. So Newton is our unit for force, meter squared is our unit for area. If I have 1 kilopascal, then it's 1,000 newtons or 1 kilonewton per meter squared. So here's our nice little conversion factor for us. 1 atmosphere, and atmosphere is another way that we can measure pressure. 1 atmosphere is the atmosphere at atmospheric pressure at sea level is 101.325 kilopascals. So again, there is a conversion factor. So 2 atmospheres, 202.650 kilopascals. That took me a second, but we got there. Okay, different ways to measure this, different barometers, there's a whole bunch of them. Millimeters of mercury was one of the original ones. So essentially we've got atmospheric pressure, so we've got all of the molecules of gas in the atmosphere looking like this, very, very nice. They're pushing in all different directions. They're pushing down on this little dish of mercury, not exactly the safest way to do it, but this little dish of mercury. The harder they push down on the dish of mercury, the higher the mercury goes up inside of this vacuum tube. So 1 atmosphere way back when was defined as when we have 760 millimeters of height for this column of mercury. So the atmospheric pressure is pushing down, causing the mercury to rise up to 760 millimeters of mercury or 760 torr. So again, here are a whole bunch of conversion factors. Again, the ones that you're going to use the most are atmospheres and kilopascals. The rest, you might see every once in a while, but atmospheres and kilopascals are the big ones. Cool. So let's skip ahead and look at this. A couple other things that we look at. So when we're on Earth, the temperature and pressure varies like crazy, right? Depending on where you go, how high above sea level you are, the weather, all kinds of different things. So there's 2 really common temperatures and pressures that we're going to use. STP is standard temperature and pressure. It is 0 degrees Celsius and 1 atmosphere. So 0 degrees Celsius and exactly 1 atmosphere or 101.325 kilopascals. Standard ambient temperature pressure, ambient meaning like room temperature is how I remember this, 25 degrees Celsius and 100 kilopascals. Now, this is another term, so 298.15 Kelvin or 273.15 Kelvin, K for Kelvin. It's another way that we can measure temperature. We'll come back to that in a moment though. Cool. So the relationship between pressure and volume. So what happens to the volume of a gas as you increase the pressure? Well, it decreases, right? So I've got this sealed container here, and I've got these masses, so I'm just going to label it with a capital M. The mass pushes down in the sealed container. It shrinks the volume to, well, let's see, this level, and we've got a certain amount of pressure. If I double the amount of mass that's on top, it's going to shrink it to a significantly smaller volume, and we're going to increase the pressure. Because again, what is pressure? It's force per unit area. So you get the same number of water molecules, or not water molecules, sorry, gas molecules in here, same number, but they're colliding way more frequently because there's way less space. Well, it's going to do two things. It's going to increase your force, and it's going to decrease your area. Both of those things would increase pressure, right? Both of those things would increase pressure. So when the volume decreases, the pressure increases, long story short. So this graph is a good graph to know. Again, as the pressure of the gas increases, the volume of the gas decreases as well. So pressure increases, volume decreases. That is the big thing, huge thing to know. Now we're going to go through and we're going to look at each of these laws. So Boyle's law essentially states the relationship. So as pressure increases, volume decreases. Here's Boyle's law up here. P1 V1 is equal to P2 V2. So pressure 1 times volume 1 is equal to pressure 2 times volume 2. That's all we're really going to talk about for the mathy part for now, because what we can actually do is just combine a whole bunch of laws all at once, right? And I think we kind of already explained this. So how can kinetic molecular theory be used to explain Boyle's law? Well, when we decrease the volume, that means that there's less space. So that equals less space. If we have less space, that means that we're going to have more collisions. So we're going to increase the collisions. And if we increase the collisions, the number of collisions, that means that we're going to have an increase in force. And of course, we know that pressure is equal to force times area. So we shrunk the area, we've increased the force, that's going to increase our pressure. Cool. Okay, next little section to talk about here. I told you we're going to fly through a whole bunch of these. So point 1, pressure and volume. Increased pressure equals increase in volume. So point 2, we want to look at the relationship between temperature and volume, right? So this is now what we're looking at. And actually, I should talk about pressure and volume. That's assuming that it's at a constant temperature. This is going to assume constant pressure. And if you want to check this one out, I mean, you won't have constant pressure for this one, but if you want to check this one out, blow up a balloon, put it in your freezer, wait for half an hour or something, see what happens to it. So you decrease the temperature. What's going to happen to the volume when you put that balloon in the freezer? Well, we're going to find out in a second here. So the relationship between temperature and volume. So here we go, same amount of pressure, that's the same mass on top, right? But at a lower temperature, we have a smaller volume. And then at a higher temperature, got that little flame down there, we've got a greater volume. Can we think about why that would happen? And let's check out some of the graphs here. So again, as you increase the temperature, the volume of gas increases as well. Now this happens differently for different types of gas, right? Like that's what we see over here, the heating several gas samples, or sorry, cooling several gas samples. So they're not all the same, but they all have the same trend, right? Increasing the temperature means increasing the volume. Now, can we think about why? Think about why. When we increase the temperature, that's an increase in kinetic energy, which in other words is an increase in speed, right? Equals increase speed. Now, picture something moving really slow versus something moving really fast running into anything, a container. Which one's going to have more force? Increase speed equals increase force. But if the pressure remains the same, that means that the container is going to be pushed outwards more, and it's actually going to expand the container. Cool. So kinetic molecular theory explains that one as well. Very, very nice. Now, something to check out from this graph again. Let me clean this up because I got writing all over it here. There we go. Is when we actually extrapolate data from all kinds of different gas samples where they have zero volume, so the volume of the gas is the same for all of them. We call that absolute zero. It is the theoretical temperature where all gases have zero volume. It is at negative, I don't know why the negative's over there, but negative 273.15 degrees Celsius, which in chemistry from here on in, we're going to call 0 degrees Kelvin. So negative 273.15 degrees Celsius is 0 degrees Kelvin. Cool. Okay, good, good. So we'll skip over that last little part here. We'll look at the relationship, Charles's law, between temperature and volume. So essentially, when we put our relationship together, this is what we need to know. V1 over T1 is equal to V2 over T2. Or in other words, when the temperature increases, the volume increases. When the temperature decreases, the volume decreases. That's the big thing. Okay, this absolute temperature scale, this degrees Kelvin. Here's a couple things that we need to know about. If I'm ever looking for Kelvin and I'm given the degree Celsius, I take my degree Celsius, I add 273.15. If I'm ever looking for my degrees Celsius, I would take the degrees Kelvin and subtract 273.15. So let's go through. Let's do a couple of these ones real quick here. Real quick. Just to make sure we're good to go with this. Okay, there we go. Get rid of all that stuff. So first one, 27 degrees Celsius. If I wanted to figure what that is in Kelvin, I do 27 degrees Celsius plus 273.15. I forgot a 1 in there. 15. There we go. So this is apparently 300.15 degrees Kelvin. Nice. Let's look at C. So I got negative 162. Negative 162, right? 162 plus 273.15 is 111.15 Kelvin. 111.15 Kelvin. Cool, let's go the other way. So let's see, where'd the calculator go there? I'm not going to do number 1, 0 degrees 7, that's negative 273. Let's do 273 Kelvin. So in this case, I'm going to do 273 minus 273.15. Nice. Oh, that's negative 0.15 Kelvin, and I think that they actually maybe just rounded off that, so about 0 degrees, not Kelvin, sorry. Celsius. Degrees Celsius. Let's do, I don't know, let's do D for some reason. Why not? So I've got 328 minus 273.15 is 54.85 degrees Celsius. I forgot the number already. Where is it here? 54.85 degrees Celsius. There we go. I'm losing it a little bit here. Cool. Hopefully that's good. Hopefully that makes sense. You do need to know how to go back and forth between the two. So let's see. I think we've already kind of talked about this, so maybe we'll skip that one over. Last one is the Guy-Lussac's law that relates pressure and temperature. All I'm really going to show you is the law right here. Pressure 1 over temperature 1 is equal to pressure 2 over temperature 2. And then we're going to jump into the combined gas law. So again, if you want to take a little bit of a break, this is a good place. This is a nice, easy spot. This is where we're going to finish things off, the combined gas law. We'll have a little bit of a lesson and then a couple examples, and then that'll be it for our first little chunk of this unit. Okay. So again, break, go for it. If not, let's hang out and let's chat. So combined gas laws. So this is all about pressure, volume, and temperature. It's combining all of those laws that we just talked about. The Boyle's law, Charles's law, Guy-Lussac's law. All combined into one law. So you don't necessarily need to remember all of them individually. Cool. So all of our formulas, again, are kind of summarized here. Here are the things that you can get away with. Instead of memorizing all of those formulas, just memorize the things that I just put in the circle. Cool. All right. So let's have a look at how. Solving gas problems. We're going to list the variables. We're going to choose a formula, except we're changing this, right? We're saying use ideal rather than memorizing, not ideal. That's coming up later. Combined. Use combined law every time. Substitute the values with the formula, into the formula with the units, and then give our answer. It's fairly straightforward stuff, right? So here's the thing. We're using the combined gas law. If something doesn't change, if something doesn't change for a question, we can cross it off. Cross it off. So we'll look at this. Example number 1. We got a bicycle pump contains 6.50 liters of air and 101 kilopascals. If the pump is closed, what is the pressure required to change the volume to 0.250 liters? Okay, so I've got volume 1 is 0.65 liters. We've got pressure 1 is 101 kilopascals, kPa. And we've got volume 2, so we're going to close the pump, push on the pump, compress it to 0.250 liters. And we're looking for pressure 2. Right, so what is the pressure required? So we're looking for pressure 2 at that 250 milliliters or 0.250 liters. Does this mention temperature at all? Even a little bit? No. So what can we do? We can assume, if it doesn't mention temperature, assume temperature is constant. Now let's go through and let's check this out. So I got P1 V1 over T1 is equal to P2 V2 over T2. Now I'm looking for pressure 2. I know that temperature 1 and temperature 2 are the same. So my first step with this, I'm going to multiply both sides of the equation by temperature 2. So temperature 2 cancels with temperature 2. Temperature 2 on this side, if it's exactly the same as temperature 1, it's also going to cancel out, right? Assuming that T1 is the same thing as T2. So if it doesn't change, you can cross it out, which is then going to give us, let's see here, Boyles's law, but we got that from not memorizing Boyles's law, just from understanding their combined gas law. If something doesn't change, why bother having it there? Cool, so we're looking for pressure 2. Let's see, I'm multiplying by V2, so I'm going to divide both sides of the equation by V2. That cancels, that cancels. I'm going to rewrite this. Pressure 2 is P1 times V1 divided by V2. So pressure 1, what did we have? 101 kPa. Our volume was 0.65 liters, and then divided by second volume, 0.250 liters. Let's plug this in really quickly. Real quick, assuming the calculator turns on. 101 times 0.65 divided by 0.25. So 262.6, I think with SIGDIGs, that should be 263 kPa. Now, last thing I'll show you with this particular example is notice liters cancels with liters. What's the only unit that we have left? Yes, kilopascals. What if I had milliliters and milliliters? So 650 milliliters divided by 250 milliliters. Let's do that again. 101 kilopascals times 650 milliliters divided by 250 milliliters. Hey, look at that. It's the exact same answer. So long story short with this, it doesn't matter what your units are for the combined gas law, as long as your units for volume are the same in 1 and 2, pressure units are the same 1 and 2, and temperature are, well actually temperature has to be in Kelvin, needs to be in Kelvin, I'll put it that way. Temperature needs to be in Kelvin. Okay, so let's check out another one. I got a couple of these picked out for us here. I think example number 2 is the next one that I want to talk about, and then just one more, and then that'll be it for the video today. So you got butane is a gas that can be used in simple lighters. Absolutely. When you go to a gas station, you get a lighter for your barbecue or for whatever, butane is the gas that's in there. So you got 15 milliliters of butane gas, so that's a volume. It says it's at 0 degrees Celsius. Okay, that's a temperature. It's warmed to another temperature, 25 degrees Celsius, and we're looking for its final volume. So let's go ahead. It looks like I'm starting with 15 milliliters at 0 degrees Celsius. So I'm going to call those 1 and 1. I end up at 25 degrees Celsius, sorry, and I'm looking for the volume at 25, so I'm going to call those 2. Perfect. Okay. So I've already mentioned this, temperature has to be in Kelvin, needs to be in Kelvin. So let's just go ahead and change that temperature 1. So instead of 0 degrees Celsius, I'm going to do, where is it there? 0 plus 273.15. Well, that's easy math, 273.15 Kelvin. And then temperature 2, same thing, except now I've got 25 degrees plus 273.15. So it's 298.15 Kelvin. Now I go back to my original equation here. So P1 times V1 is equal to, divided by T1 is equal to P2 times V2 over T2. Now what doesn't change in this question? What is constant? It's the volume and temperature changing. It's the pressure must be constant. The pressure is constant. So that means that we can get rid of pressure if pressure is constant. So I'm just going to rewrite this for the sake of neatness. V1 over T1 is equal to V2 over T2. Okay, I am looking for V2. That is up here. I'm dividing it by T2, so I need to multiply both sides of the equation by T2, following our normal rearranging rules. So those cancel. I end up with V2 is equal to T2 times V1 over T1. We can plug in some numbers here. So T2, let's see, 298.15 Kelvin times the original volume, which was 15 milliliters, and then divided by our initial temperature. Let's see, our initial temperature was 273.15 Kelvin. Let's go ahead and plug this in. 298.15 times 15 divided by 273.15. Let's see, 16.37 with sig digs. I think that's just 16. And then what's the only unit that's left? So Kelvin cancels with kelvins. The only units that's left is milliliters, so that'd be 16 milliliters. Perfect. Okay. So what assumption did we make? Pressure was constant is one of the big things that the big assumption that we made there. Absolutely. How does this calculation illustrate the need to use absolute or Kelvin temperatures? So let's say that we plug these in with degrees Celsius. You do 25 times 15 divided by 0. That ring any bells for anybody? You can't divide by 0 is one of the big things that we look at for this. That's one of the reasons why it needs to be in Kelvin. Okay, one more quick example here. One more just to highlight something. Okay, it's number 6 that I want to check out with you. Number 6. So a cylinder of helium gas has a volume of 1 liter. The gas in the cylinder exerts a pressure of 800 kilopascals at 30 degrees Celsius. What volume would this gas occupy at SATP? Okay, this is a lot, right? So let's see. V1, I'm going to say is 1 liter. Cool. P1 is 800 kilopascals. And then T1, well, it's 30 degrees Celsius, but we don't really want 30 degrees Celsius. So let's go ahead and do 30 plus 273.15. Nice. 303.15 Kelvin. Okay, nice. What volume, so my goal is to figure out V2, would it occupy at SATP? Now at SATP, we just talked about that a few minutes ago. You might not recognize that as anything in particular yet, but as soon as I see that, I see 25 degrees Celsius. I'm going to write that out, 25 degrees Celsius at 100 kilopascals. 25 degrees Celsius at 100 kilopascals. So T2 then is going to be 25 degrees Celsius. We want that in Kelvin. 273.15 plus 25, 298.15 Kelvin, and then P2 is 100 kPa. Perfect. Now I think we've got enough information. So I'm going to start with my combined gas law. P1 V1 over T1 is equal to P2 V2 over T2. Perfect. everything changes in this case, so we can't cross anything out. So let's rearrange and let's solve for V2. So I'm dividing by T2. That's T squared. That's not at all what I want. T2. So multiply both sides of the equation by T2. Excellent. And I'm multiplying by P2, so I have to divide both sides of the equation by P2. Now I got a huge mess. So I'm just going to rewrite this. V2 is going to be equal to T2 P1 V1 over P2 T1. Nice, we just got to plug in numbers. So temperature 2, 298.15 Kelvin. Pressure 1 was 800 kilopascals. Volume 1 was, oh, that's easy, 1 liter. And then divided by pressure 2, which we said was 100 kPa. And then also divided by, let's see, temperature 1, which we said was 303.15 Kelvin. Okay, let's go through here and let's just plug all those numbers in. 298.15 times 800 times 1. I guess I don't really need to times by 1, but whatever. Divided by 100. And also divided by 303.15. There's many different ways that you could plug that in. Just make sure that you are getting to our answer of 7.9 liters. 7.9 liters. Cool. All right. The last one that I kind of want to look at is just example 7. What assumption is made in all of the previous calculations that we've done so far? Every single one of them. Here's the big thing. The type of gas doesn't matter. We talked about butane gas. We talked about, what was this one? Helium. It could be oxygen, could be nitrogen, could be methane. It doesn't matter. The type of gas doesn't matter. These formulas all work out because every gas at the same temperature and pressure has the same volume, which is kind of wild, right? Kind of wild. Anyways, I know that's a bit of a long one. Good job, folks. Good job for sticking with it. Make sure you try out a bit of practice. Again, this is just practice until you're comfortable with it. You don't have to necessarily do all of these practice because there's quite a few of them. But please do practice on the next couple pages here. I mean, a ridiculous amount of practice. Up to page 18. But again, you do not need to do every single one of these questions. You need to work on them until you get the idea. So maybe try every third one, every second one, something like that, every fourth one even. Like, there's a lot of questions. Do it until you're comfortable with it. Anyways, that is it for now. We'll talk to you again soon. Bye-bye.